If it is diagonalizable, then the minimal polynomial is x, which
Yeah.
implies that operator equal to 0 operator.
Yes, yes. This is non-zero, therefore t is not equal to 0. And this is nilpotent, therefore there exists a least positive integer m which is greater than equal to 1, not equal to 1 rather, greater than 1, which is 0. That means mtx is not equal to x. Therefore, this is not diagonal. Yeah, that's right answer. All right. Hello.
Yes, sir.
That is all right. Now we go to the next part. This next canonical part of this. This is one of the canonical forms. So next theorem says, suppose sometime you don't have empty x which is having linear factors. Say x minus lambda I square or lambda k is of this kind. Then obviously t is non-diagonalizable. Then t is non-diagonalizable. Okay. But in that case, what we try to look at, we will be trying to look at in that case a canonical form which would be near to your diagonalization. So that's now the result we are going to do. Here is this theorem. Let V be a finite dimensional vector space over F. Finite dimensional vector space with, say, dimensions equal to n and t belonging to LV. LV is the set of linear operators. Then the following are equivalent. What are those? Now we are coming to the triangulable. So we are looking at the triangularization of an operator. Okay. CTX, which is characteristic polynomial of T, splits over F. Second part is every non-zero T invariant. T invariant means T invariant subspace. T invariant subspace means W is a subspace of V such that TW is contained in W. That is known as T invariant subspace. V contains an eigenvalue of T. Third part is tree is triangulable. In this case, T will be triangulable. It is not diagonalizable now. If it is not diagonalizable, then if this happens to be true, then T is triangulable. All right. Is the concept is clear with you? What I'm trying to prove? Hello.
Yes, sir.
That means now we are not talking of the minimal polynomial here. Whatsoever minimal polynomial may be, if that is splitting into the distinct linear factors, this would be diagonalizable. If not, then it is triangulable. All right. So let us now look at one. If one is true, we shall be proving that 2 is true. 1 implies 2. So for that, let W be a subspace of, be a T invariant subspace of V. All right. If W is T invariant subspace, then there exists an operator T1 from W to W, right, which is an induced operator of T. Operator of T. That means whenever you define T1W something where W belongs to W, then this is same as T of W, right? This means this is induced operator, all right? Also, if this is induced operator, since I had somewhere shown you, if this is a T invariant subspace, then yeah, let me write here. Okay. This is T invariant subspace. Then the matrix of T with respect to a certain basis would be of the kind T1 under the basis B1. B1 is a basis of W. Here, this is T. Let me have this T cap B2 0 0. T cap is induced operator on V quotient W. All right. This is a result. You can look at that in the basic results of the vector spaces. All right. Then the matrix of T would be that. Here B2 is the basis of V by 2. All right. So now this immediately provides me that CT1X divides the CTX. This is a factor of CTX from here. All right. If this splits, then obviously then so is, if let me write now, if CTX splits, then so is CT1X over F. All right. And suppose X minus lambda 1 is the factor which is of CT1X, right? X minus lambda 1 is the factor of CTX. That means lambda 1 is the eigenvalue of, that is, lambda 1 is an eigenvalue of T1, which means what? There exists a vector, non-zero vector, W1 say in W, such that T1 of W1 is exactly lambda 1 times W1. Sorry, let me 1 times W. But this is an induced operator, so this is same as that of T of W1. If this is happening true, that means lambda 1 is an eigenvalue of T, and W1 is eigenvector corresponding to this lambda 1. And this is an eigenvector which is where in W. This is an eigenvector of T. So this meets the second part which we want to prove. All right. Then we come back that 2 implies 1. 2 implies 1. So for 2 implies 1 means we are now assuming that every non-zero T invariant subspace of V contains an eigenvalue of T. Yeah. We have to prove that CTX splits. So for that, what we do? We shall be assuming now, let QX be an irreducible factor of CTX. Irreducible factor, it may be of degree 2, it may be of degree 3, it may be of degree 1. If it is of degree 1, that means CTX is splitting. All right. Irreducible factor, if it is of degree 1, that means CTX is splitting. So we have to prove finally that QX, which is an irreducible factor of CTX, which we have assumed, is none other than a linear factor. Okay. So we consider now a subspace W, which is exactly kernel of QT. Now, primary decomposition theorem says that if this is an irreducible factor of CTX, this would be certainly occurring in the MTX also. So therefore, this kernel, which is in the decomposition of V, would be non-zero. This is non-zero T invariant subspace. T invariant subspace of V. All right. And then by 2, this must be containing one of the eigenvectors of T. Hello. Hello.
Yes, sir.
Yes, sir.
So this is T invariant subspace. Therefore, W has an eigenvector of T. This is second part. Therefore, W has an eigenvector of T. Eigenvector of T. All right. That means W, if this vector is, say, W1, let us take W1. That
Hello.
is, yes, hello.
But how kernel of Qt is non-zero?
Because of the primary decomposition theorem. This is an irreducible factor
Yes.
of CTX, so it would be occurring in the MTX also. And if it is occurring in the MTX, then the kernel of Qt is non-zero and occurring in the decomposition of V. All right. Hello. Hello.
Yes, sir.
Okay.
No, sir. I don't get it.
I am utilizing primary decomposition theorem very
Yes,
heavily, which I did in the first lecture.
Yes, I have attended that lecture also.
So there we just decomposed our V.
Yes.
So this is a vector W1, which is non-zero, is an eigenvector of T. So that means TW1 is equal to some lambda of W1. Lambda belonging to F. All right. But this is T invariant subspace. Therefore, there exists an induced operator T1. Induced operator T1 on W, which says that T of W1 is same as T1 of W1, which is same as that of W of lambda of W1. All right. All right. Hello. Hello.
Yeah, okay, sir.
Okay.
Yes,
And
sir.
again, we are recalling our primary decomposition theorem. T1 is an induced operator now on W. W is kernel of Qt. All right. Then what is the minimal polynomial of T1? This is QX. Remember that? Hello?
Yes, sir.
Okay.
Yes, sir.
And if this is the eigenvalue of T1, is it not the root of MT1x?
Yes, sir. X minus lambda divide QX.
Divide. So if x minus lambda divides qx, that means qx is being splitted. Because qx was initially taken as irreducible factor. Is that okay?
Okay, sir.
What that leaves? This leaves that qx is none other than, this is, if we just assume that this is irreducible factor, this is none other than x minus lambda. If x minus lambda divides qx, qx is irreducible factor, then certainly qx has to be x minus lambda. And this is our goal. All right. So this implies 1 is over. Okay. Now we have to prove 1 implies 3. So what is 1? 1 was that CTX splits. CTX splits over F. All right. We are to prove now that T is triangulable. So we shall be using induction here now. Induction. All right. On what? Induction on N, which is dimension of V. Right. If N is 1, then obviously statement is true. T is any operator, then what would be the matrix of T? It is 1 by 1 matrix. It is 1 by 1 matrix. Okay. Hello. And in that case, T is
Yes, sir.
triangulable. In
Yes,
that
sir.
case, then T is triangulable. All right. And let us suppose no. Yes. Hello. Hello.
Sir, can you please statements first?
Your voice is not clear. Please speak out again.
Can you please show the statements?
Yes. Let me show this statement. These are CTX splits over F. Every non-zero T invariant subspace contains an eigenvalue of T. We have already shown that 1 implies 2 and 2 implies 1. They are equivalent. Now we have to show that 1 and 3 are equivalent.
Yes, sir.
All right.
Thank you.
Okay.
Yeah.
So if the dimension is 1, then obviously T is triangular. Let us suppose that the result be true. The result be true for all vector spaces with the dimension less than or equal to n minus 1. All right. And since now dimension of V is given to be n and CTX is splitting, CTX splits over F. Let us suppose one of the factors is x minus lambda. All right. Then let x minus lambda divides this CTX, then lambda is eigenvalue of T. All right. If this is an eigenvalue of T, then there exists a eigenvector in V such that TW is lambda of W. All right. And then this W is certainly linearly independent. I may take a vector space which is generated by this W. All right. This is T invariant subspace. Is T invariant subspace of V. All right. And I can extend this basis to the basis of V also, W. If I just take x2, xn, this is a basis of V. But then certainly if you look at x2 bar, x3 bar, xn bar, which I just denote by B1, this is a basis for V by W. You can check that when we prove the dimensional formula. That means dimension of V is same as dimension of W plus dimension of V by W. There we prove that this is a basis of V by W. Okay. Right. And since this is also T invariant subspace, W is T invariant subspace, then you have T cap as an induced operator on V by W, induced operator on V by W of T. T cap. T cap is a induced operator of T, and CT cap, I just above the result I could show that this divides CTX. This is also holding. And if CTX is splitting, then obviously this is also splitting. And if this is splitting, this is the basis of that. And the dimension of this is n-1. From here, you just count down. The dimension of this is n-1. Therefore, what happens? By induction, the matrix of T cap with respect to this basis is triangulable. Okay. Hello? Triangulable. And what is that matrix look like? It would be looking like this way. Some alpha 2 to 0 and so on 0. Some alpha 2, 3 and some alpha 2 n. Here again you get something alpha 3. Let me take this is 3, 2, 3, 3 and so on 3 n. And this alpha and n. Right? But what does that mean? This means T cap of x2 bar is what? This is alpha 2 of x2 bar. And similarly, T cap of x3 bar, sorry, x3 bar. This is alpha 2, 3 x2 bar plus alpha 3, 3 x3 bar. This is what it means. Continuing like that, we can generally write this T cap of xj bar, which is given by j starts from 2 to, sorry, I starts from, let me, yeah, J I have taken here, so I should not take J here. I starts from J2 to J. This is alpha ij xi bar. Most generally, we can write this way. And remember, because this is a basis of V by W, so therefore xi bar, here xi bars, they can be written as xi plus W. All right, quotient space is the space of such type of elements. Okay. And hello, yes, please. Hello.
No, sir. Right.
Right.
Space.
This means what? T cap. This is induced operator of T. Right. This means what? This is same as T of xj plus W. This part is same as writing here alpha ij, j starts from 2 to, sorry, I starts from 2 to j. I starts from 2 to j. xi plus W. I can write this way. Okay. Using such things, you can. This is the induced operator, action of induced operator. And two cosets are same if and only if Txj minus I running from 2 to j alpha ij xi, this belongs to W. But W is generated by W1 only. This means this is true for j starting from 2 to onwards. Look at that. Right? This is true for all j's. 2, 3, and so on. And okay. And this last equation provides me this Txj minus summation I running from 2 to j alpha ij xi. This is none other than alpha 1j W1, because this is an element of W. And W is generated by W1. And therefore, what happens? T of xj is equal to this alpha 1j W1 plus I ranging from 2 to j alpha ij xi. This is j is now starting from 2 to n. And if I just look at, sorry, this W1, x1, I just take as W1, which is, let me write W, not x1. W1, I just state that this is alpha 1 of W1. All right. Then my T is now defined for all xi's along with the W1 as this. And this definition is now immediately providing me the matrix of T with respect to basis B, where B was none other than this basis. If you look at that, this is the basis of B. W, x2, xn. All right. This is acting on the basis elements. Then what is the matrix of B, T, with respect to this basis? Can you tell me? Hello.
It's
Hello?
A11, A12,
Alpha 1, 1.
alpha 11, alpha 12 dot alpha 1n,
Yeah, very
0,
good.
alpha 22.
Alpha 2, 2, and so on. This is the same matrix as that of T cap. Here you are getting. All right. So this way you are getting alpha n. These are zeros. And this means T is triangular. This means T is triangular. This is what I wanted. This completes the proof. Now we are to prove that 3 implies 1. 3 means T is triangulable. That means the matrix of T is like that. Then we have to prove that CTX splits over F. Is that clear or not? From here.
Yes,
3
sir.
means this. I want to prove 1. That is this. Is that clear from here or not?
Yes, sir.
So CTX splits from this. All right. So this proves that if MT is not factored into distinct linear factors, then it is triangular. Then it is triangular. Then we can triangularize this.
Sir,
Yes.
can you please come to the proof of second implies one?
Second implies. Yes.
One.
Let me come. Second implies 1. Oh.
So the first
one second,
statement was that CT should split in linear factors, right?
Second implies 1. This one.
Yeah.
Yes.
So the first one is that CT should split in the linear factor. So you are taking the irreducible factor.
We are to prove now that CTX splits.
Yeah, but you are using the primary decomposition.
No, not here. We
Not
are now.
here you have only taken the irreducible factor. Then you consider
that should be rather monic. If you take monic, then it would be very good. Okay. Yeah. Chaliye. Yes.
Yeah. So in the below you are using the primary
Yes.
decomposition. Right?
Here I just say this is W, which is kernel of QT. This is an irreducible factor. Would be certainly a part of MTX also. All the irreducible factors of CTX, they are also the part of MTX. This is Cayley-Hamilton theorem.
So you are also using the Cayley-Hamilton, right?
Yeah, that comes into the play. Okay. So this is the subspace which comes in the decomposition of V, and so this is not zero. All right.
Sir, Cayley-Hamilton only says that CT will annihilate the T, right?
CT?
The characteristic polynomial will annihilate the operator T. That is a Cayley-Hamilton, right?
No. That says MTX divides CTX in the operator theoretic method. That is same as what you are saying, in fact.
Yeah. So then it will imply the irreducible factor of CT will also be the irreducible factor of MT.
Yes, exactly.
Okay, I think this is okay. Yeah, but we have not proved the Cayley-Hamilton, so we are assuming that one.
In 2-3 lectures I cannot complete the whole course. I can
No, that is okay. I'm just I'm just trying to see what we are all using in this fact. So we are using Cayley-Hamilton as well as the primary decomposition.
Yes, exactly.
Yeah.
Primary decomposition theorem heavily.
Yeah, right.
Heavily. Otherwise, you can utilize this. You can prove this also at your own also. How? If QX is the irreducible factor, say, then this cannot be factored or into linear factors. Okay. This cannot be factored further. Irreducibility means this cannot be factored further.
Yeah,
Hello?
that is okay. Yeah,
Okay.
that is okay.
Now, if you look at that, see, I just prove one result here. Let me just take sideways. Here, yeah, here. Let me write. If fx is any polynomial, right? Fx is any polynomial. Then you look at ft. This is an operator. If you apply this on an eigenvector of T, V is an eigenvector of T, then what does that mean? What does that mean? Hello?
It will be just eigenvector of ft also.
No, this is f of lambda
B.
into V, where lambda is eigenvector, of T corresponding to eigenvalue lambda. Okay. Right? Hello.
Yes,
sir,
sir.
it's okay.
Okay. Now, if Ft is a characteristic polynomial, Ct, this is true for all polynomials, then this is Ct lambda of V. But characteristic polynomial is 0, right? Is it all right?
Yes, sir.
Therefore,
Yes,
what
sir.
happens here? V is non-zero because this is an eigenvector. That means Ct lambda is 0. That means lambda, whatever the eigenvalue, would be the root of Ctx. And same fact would be applied on mtx. This lambda is also the root of mtx. All right.
Yes, sir. Yes, sir.
And what that says, if some irreducible factors, this is occurring here in Ctx,
It should occur in empty.
mtx also.
Yes, sir.
That comes from here also. Okay.
Yes, sir.
Yes, sir.
That's it. So this is how we could do the triangularization. All right. And then we come to our most wanted canonical form, which is known as the Jordan canonical form. Right. For that, we are now just coming. For that, what we look at, what happens? See, diagonalization and triangularization. These are two canonical forms. Something which is more closer to the diagonalization is the Jordan form, which is better than triangularization. Look at that. How can we do that? This is also Jordan form can be obtained in the same conditions as that of the triangularization, but it is better than triangularization. Triangularization means the matrix of T would be upper triangular or lower triangular. If it is upper triangular in Jordan form, it would be containing Jordan blocks on the diagram. Jordan blocks means maximum entries in the upper triangle are also, they are 0. All right. So now we are going to just get that Jordan form, right? See here. For that, we are now defining something. T is a linear operator, right? V is a finite dimensional vector space. Say, let us say dimension of V is n. Then what we do, we are looking at kernels of T minus lambda I raised to the power R, where lambda is an eigenvalue of T. R is positive integer. R is non-negative integer, you may say. Non-negative. That means we are including 0 also. Okay. Look at, if I just define this by E lambda R, then my E0 lambda I conventionally take as.
Sir, R cannot be 0. No?
Hello.
Sir, R cannot be 0.
So I have taken 0. 0 means this is 0 vector. 0 vector space. All right. Hello. I conventionally take R0. For that, E0 lambda is 0. Hello.
Yes, sir. Yes.
Okay, okay. Okay, sir.
What do you mean by E1 lambda? This is kernel of T minus lambda. That means this is eigenspace. eigenvectors, which consists of the eigenvectors. So that means, what do you mean by E2 lambda? This is t minus kernel of t minus lambda I square, and so on. Look at, we are getting a chain like this, 0, which is E0 lambda, contained in E1 lambda. This is contained in E2 lambda, and so on. Is that okay? Are you convinced with that?
Yes, sir.
But we see, this means what? The dimensions of each EI lambda is increasing. If this is strict, if the inclusion is strict, let me write this way, then this would be the dimensions of E lambda i's are increasing. This means they are increasing. Is it okay?
Yes, sir. Yes, sir.
But this cannot go beyond a certain integer. So somewhere this would have to be same as that of ek plus 1. Why? Why? This has to be equal.
Finite dimension.
Because V is finite dimensional vector space. Due to that control on dimension of V, we have to get some chain is terminating somewhere. All right. All the time, this is eigenspace containing all the eigenvectors, but these may not be the eigenvectors. They are basically known as, this is known as generalized eigenspace. Generalized eigenspace of order R. All right. All right.
Yes, sir.
If I just take X, which is belonging to ER lambda, but not in ER minus 1 lambda, then X is known as generalized eigenvalue of order R. All right. Corresponding to eigenvalue lambda. All right. Let me now look at something here. What can you just say t minus lambda I applied on X if X is here? If X is here, what is the guess for that? Where this vector would be? Is that all right or not? Hello?
Yes, sir. Yes, sir.
It would be there. What can you guess this?
ER minus 2 lambda.
Yeah, R minus 2 lambda. And if I am going on increasing these powers, let me just say this is up to R minus 1. Where this goes?
E1 of lambda.
E lambda. E1
E1 of lambda. Yeah. You can just look at this thing. Right? This is an eigenvector. This means this is an eigenvector. All right.
Yes, sir.
Now we are going to define something here, which is known as Jordan chain. What is that? I just take a collection of the non-zero vectors. These are all non-zero vectors. All non-zero vectors in B. All right. Right. Such that T of x1 is equal to lambda 1 x1, where lambda, let me take lambda. I have not take lambda 1. So this is lambda. T of x2 is something lambda times x2 plus x1. T of x3 is lambda x3 plus x2, and so on. T of xk is lambda of xk plus xk minus 1. Can you see if this is the collection of vectors satisfying this condition? Then this means equivalence. Let us look at the equivalence. T minus lambda I of x1 is 0. That means x1 is an eigenvector. This means T minus lambda I of x2 is x1. This means T minus lambda I of x3 is x2. This means T minus lambda I of xk is xk minus 1. Can you further look at some relations? Yes, I can. See, if I apply
T
here,
minus lambda I 2 x2 equal
here
to 0.
x2 would be 0.
T minus
T
lambda
minus
I
lambda I
3
cube
x3.
x3 is 0. See, whatever the index here, if that is the same power as that of this, then that is 0. So here T minus lambda I raised to the power, yeah, what should I take now? K. Xk is 0. All right. Here this is 1, 1. So x1. You are getting this relation. All right. Now we are going to prove a proposition. Such type of vectors.
Excuse me, sir.
Yeah, please.
How are you taking these x's? Like
These
you
x's are right now we are just randomly choosing such that we are satisfying this. We shall be in search of such x's. Why? The reason comes just after proving something.
okay, sir.
Okay, you just wait down for that reason. So the collection of such vectors, non-zero vectors, which are satisfying these relations, is known as Jordan chain. Known as Jordan chain. We are going to prove that every T which is triangulable can be the matrix of that T can be a Jordan matrix. Okay. So this is known as Jordan T, a Jordan chain. Now our proposition is that a Jordan chain consists of linearly independent vectors. means these are none other than linearly independent factors. So for that, if I don't want to prove this, so how can I prove this? I want to prove that these are linearly independent. Non-zero is already taken granted by definition. So what I look at, if I just take, if alpha xi, I running from 1 to k is
Equal to
0,
zero.
implies alpha
Always
is 0 for all x. This is what I wanted.
Yes,
Okay.
sir. Yes, sir.
All right. So suppose, let us suppose this R be the largest index, such that alpha R is non-zero. Contrary, we are proving this result. Suppose there is the largest index R such that alpha R is non-zero. Then what I do, I can write this equation as XR here and
That's
here
a linear combination of rest of all.
rest of all. I running from 1 to R minus 1. Alpha R inverse, alpha I xi. This is R minus 1. This is R minus 1. All right.
Yes, sir.
Now, utilizing the things we have just shown above, t minus lambda I raised to the power R minus 1 applied on xr. What are you getting this? Look at that.
0.
Not 0. This is 1 power less.
One less power. Yes, sir.
So what happens? From each of this, what can you say?
Previous one.
T minus lambda I raised to the power R x R minus 1 applied on xr.
Right hand side is 0. I am telling about.
No. This is R minus 1. This is, if this is R, then it is 0. From here, this is x1. Check. If I just apply
Yes,
1 power less, here 1 power less. If you just take 2 here, then it would be what? x1.
X1.
Yes,
x1.
sir.
Is it okay?
Yes, sir. Yes, sir.
What about the other side? Because if you take the same power as that of index or larger power, then it is 0.
0, yes.
Okay. Right side would be certainly 0. This side would be certainly 0. And this side is x1. This would give you x1 as 0. While
Zero,
x1 is non-zero.
Non-zero set of vector. Yes, sir.
Therefore, contradiction.
Yes, sir.
Which is a yes, sir.
Therefore, what happens? Jordan chain is always linearly
Independent.
Independent.
always linearly independent. Okay,
Yes, sir.
linearly independent. Now, this is giving you another information. What can be the largest size of Jordan chain? I just say if this consists of k vectors, then I say this is the Jordan chain of length k.
Okay.
What can be the largest size of the Jordan chain?
N.
Largest independent.
Independent. So that is the dimension of V.
Dimension.
So if some Jordan chain consists of the basis elements of, say, this is Jordan chain. Let me not write this Jordan chain this way. Let me say, if this is the Jordan chain, length n for V with dimension n, then this is a basis of V
Yes, basis. Yes, sir. Largest independent.
with respect to T. है ना?
Yes, sir. Yes, sir.
T. And can you just tell me what is the matrix of this T with respect to this basis?
Diagonal.
Lambda on the diagonals
It
and
will be diagonal.
This is first
one on the
lambda,
super
yeah,
diagonal.
diagonal, and one on
One on the
the
super diagonal.
not super diagonal. This is here. Rest are zeros because you look at
Sir, will it be subdiagonal or super diagonal?
subdiagonal. Look at that.
X2 is x2 plus x1, right? So it should be above.
So this is this is
But
above. Yeah.
It will be upper diagonal, right?
Upper diagonal.
Upper
Okay.
triangular.
Okay, no problem. Yes. Yeah. This is yes. Right. You are right. Here. These are super die. Rest are zeros. All right. And this
Yes,
is
sir.
called Jordan block. Jordan block with respect to eigenvalue lambda. It may be of order k also. It may be of order n. Now we are interested in a general T which is not diagonalizable to find out a basis B of V such that the matrix of T are Jordan blocks. Let me just write here K1 lambda 1, or say they may be different also, right? JK 2 lambda 1 and so on. J lambda j, sorry, JK, and rest are zeros. Then the matrix of T would be looking like this way. Some lambdas here. If lambda 1 I put here, ones here, zeros here, and then second matrix again with respect to lambda 1, but is of order K2. Ones, zeros here, and so on. This way we want to decompose the matrix of T. Right? Basically, vector space. When we decompose the vector spaces, that means we are playing with the matrices. That's it. This is a connection between the decomposition of the vector spaces and the matrices. We are finding the bases such that they are written in a certain form which we wanted. All right. So I think time is not much enough. I cannot be able to prove the existence of the basis. So next time I would be proving. There is one more lecture on 14th. In that lecture, we shall be proving the existence of the Jordan basis, and then we'll be going ahead. Okay. All right.
Okay. Yes.
Okay. Done now. If any question is there, you can ask. Hello.
Yes, sir.
Rajesh ji. Hello, Rajesh ji. Hello.
Excuse me, sir.
Haan ji.
Can you please upload these notes and the notes of previous lectures on Dropbox?
I may try. I would be. Okay.
Okay, sir. Okay, sir. Thank you.
Thank you, sir.
Okay.
Thank you, sir.
Okay. Bye bye. Hello, Rajesh ji.
Excuse me, sir.
हाँ जी.
Sir, can you please explain the step where T is triangulable implies that CTX splits over A?
Yeah, I just said that. Why didn't you put me question there? Let me go there. Yeah. What you wanted now? You tell me.
Yes, sir.
What is the need? This one?
3 implies 1.
This is easy from here. See, for triangular matrix, these are the eigenvalues.
Okay, sir, got it.
Got it? All right.
Yes, sir.
Any other?
Oh, sir, complete lecture?
Hello.
Yes, lecture is complete.
हाँ जी, प्लीज। मैं
Okay.
वही आपको
Thank you.
ओके, बाय बाय।